Hello, so my name is Hélène Plisnier, and this work is in collaboration with Dr. Steckelmacher and Professor Nowé. And the three of us are affiliated with the Vrije Universiteit of Brussels. So first of all, I'm going to talk a little bit about how transfer learning in reinforcement learning context often works, and then I will introduce our contribution. So in general, in reinforcement learning, when we do transfer learning is to learn a target task faster. So we have our agent learn a source task, a first task from scratch, and we hope that by some intelligent way, our agent will be able to use some of the knowledge that has learned in the source task while tackling the target task. And so to learn that target task faster than by directly trying to learn the target task from scratch. There's no clear consensus on how the source and the target must differ. It is often the case that they are different. The source and transfer and target task are fairly different. Maybe the source task is a bit simpler than the target task, and the target task more sophisticated. But they should be, they're often related. Otherwise, it's really difficult to transfer anything from the source to the target. I've seen some work trying to make some rules about how similar the tasks must be. For example, you can assume maybe that the robot on which the agent is uploaded and is executing its program, the robot platform is the same. So it has the same effectors. You can at least assume that it has the same effectors, so the same kind of actions, and also the same state description, so the same sensors. But if you manage to have a robot on a given robotic platform help, so the policy learned on that robot help another robot to learn something, another task, or you have an agent that has learned to swim. If you can manage to transfer some knowledge from swimming to flying, for example, even though these two tasks seem very different, good for you, obviously. People will applaud you. In this work, so this is just some of my own terminology, I'm often going to talk about the agent that is learning the source task as the advisor, and then the agent that is learning the target task, I'm going to call it the advisee. Now, transfer learning in reinforcement learning is a fairly messy field. There's a lot of work out there doing a lot of different things, and it's hard to categorize this work. First of all, because you may have a lot of transferables, a lot of different components that are being learned by a reinforcement learning agent. You may have some parts of the neural networks that you want to transfer, but not other parts. If you have sophisticated neural network architectures with several bits to it, you may just want to transfer the whole policy directly, but not your critics if you have an actor-critic algorithm. And then the ways to transfer these components, these transferables, also may differ. So you have a lot of different combinations of the transferables that you consider and the technique that you use, the different techniques. What we are going to look into in this work, so I'm going to transfer the policy of an advisory policy. This is the policy learned on the source task. We're going to transfer that policy using a policy shaping technique. The two techniques that we are going to review and compare here is probabilistic policy reuse and policy intersection. These techniques are not new. So PPR is from 2006 by Fernandez et al. And policy intersection is by Griffith et al. In 2013. Probabilistic policy reuse looks a lot like epsilon greedy. So what I didn't say before is that often policy shaping can also be called guiding the exploration strategy. So these are techniques that are used in the action selection part of the agent. So during action selection, instead of sampling an action from just the currently learned policy, sometimes with a small probability psi, I will sample the advisory policy. So it looks like a lot like epsilon greedy. So, but in some random probability, I will take actions from the advisory policy with a small p probability. It's often also considered that this PA is fixed and frozen when you reuse it, so you don't update it again. Same thing in policy intersection. The difference between PI and PPR is that in policy intersection, at each time step, you sample your action from the mixture of the advisor policy and the advisee policy. So you multiply, you have two vectors. So this is in the discrete action case here. We look at the environments in which the actions are discrete. You have at each time step two vectors that represent the state-dependent policies of your advisor and your advisee. So you multiply these two vectors together, both vectors of floats of the size of the number of actions that you can take, a finite number of actions because the actions are discrete, and then you normalize that new vector so that it still sums to 1 and works as a proper policy from which actions can be sampled. So this acts as a logical end between what the advisor would like to do and what the advisee would like to do. It's an intersection between the two. So to wrap things up, so in transfer learning in general, what people often do, is that they have a first agent training on a source task from scratch. This agent, you can train it for how long you want, however long you want. It can be a short while or until it gets confident. And then you copy it in some variable. Here we work with self-actor critic. So I will save my actor in an advisor variable, and I can throw away my critics. What I want is to have a pie that I can sample actions from. And then this pie, I freeze it. I never update it again. And then I have a new agent, fresh agent, that is my advisee, that is going to train on the target task until it gets to a good policy, so until it gets confident this time. Always. And here on this arrow is where you have your transfer learning algorithm, so your PPR or your PI, your probabilistic policy reuse or policy intersection. So now our scheme is a little different because instead of having a source and a target task, which are two different tasks, the source and the target are actually the same task. And what we do is that we train our advisor for a very short while, and then we save it. And this agent, the advisee, will train for as long as it takes to get a good policy. And so we have this this frozen advisor that hasn't been trained for very long, advising the advisee on the same task. Now you may wonder why this is interesting. You may think this is pretty redundant. Why transferring knowledge from a task to itself? Now we have two hunches. First of all, we have different levels of training between the advisor and the advisee. Since we have fixed this advisor, we never change it again. It still is, and we have trained it for maybe like 20 or 40 episodes, while we would need thousands of episodes to actually get a good policy on this task. So it gets trained for a very short while. So it still wants to explore a lot. While this advisee gets more and more confident in the task and might need some extra exploration, might want to explore it too much. So we have this push for exploration coming from an advisor because they have different levels of training. And also, we have initialized them differently. So the initialization of their neural network weights are different. And this may contribute to a different experience of the same task in the same environment. So the advisor and the advisee might have learned, even though they're trying to learn the same task, because of their initialization that is slightly different. Each time it's a random initialization of the neural network weights. They may have accumulated a slightly different experience of the same task. They might have learned a slightly different policy. And so they their knowledge might be slightly complementary to each other. And this is actually, sorry, suggested by a fairly recent paper called Dual Policy Distillation, which launches two agents in two separate instances of the same environment. So they both learn in parallel, and they distill their policy in each other's. And they have a theoretical justification as to why these two agents, by learning parallel but having two distinct initialization, their knowledge then becomes complementary and they can help each other get a better performance, in contrast to having just one agent learning a task. Now we're going to see some results. On 3, we're going to test self-transfer on 3 environments, with continuous actions, pi bullet environments, so hopper, half cheetah, and ant. But before we can see some results, we need to adapt policy intersection for continuous actions, because for now it only works with discrete actions. This multiplication between two vectors of probabilities only works when you have two finite vectors of probabilities, because you have a finite amount of actions. But when you deal with continuous actions, your reinforcement learning algorithm will often only output, it will predict one action, which is a float, because there's an infinity of different actions that can be executed by the agent. You don't have a nice, neat, finite amount of actions. It can be an infinity. So here, the idea of how it works, how we dealt with that problem, to still have an intersection between what the advisor and the advisee want to do, is we sample a whole bunch of actions from the advisor. And then for each of these actions, we ask the policy of the advisee the probability that it would have given that action. It would have, with what probability it would have this particular action coming from the advisor, with what probability it would have been sampled from the policy of the advisee. So now we have a vector of probabilities corresponding to the vector of actions here. And a lot of them might be above 1. They don't sum to 1, and they certainly don't represent the whole policy, the whole probability distribution over all actions. They're just a sample. We just have sampled a bunch of actions, a few actions, and got a probability for each of these actions. And now we want to sample one of these actions to execute it. To bring these probabilities here to values between 0 and 1, to floats between 0 and 1, we divide each element here by the maximum element of this vector of probabilities. And there's a lemma by authors whose name I forgot, unfortunately. But they are cited in the paper that says that if we do that, we get, instead of probabilities, we get a vector of possibilities, which belong to the realm of fuzzy set theory, which I'm not so familiar with. But so these possibilities are between 0, they're floats between 0 and 1, sorry. And now we can sample an action from the vector of actions here by looking at its possibility. And if it satisfies this condition, so the possibility for this given action from the set of actions here is, if the possibility is above a randomly generated float between 0 and 1, we take this action. If, after having tested all these actions from the advisor, we don't get one action that respects this satisfies this condition, then we give the last word to the advisee, with just sample an action from the advisee. Now for some results. So we have PPR and policy intersection, both implemented on top of SAC with 2 different advisors. We tried an advisor with 100 episodes of training and one with 200 episodes of training. These are averages over 8 runs each. Each of these curves are at least 8 runs. And here we have some lines representing the amount of time that each advisor has taken. So here we have the curves of advisors that have been trained for 100 episodes. And then after that, the curve corresponds to the advisee learning. So while being helped by this advisor trained for 100 episodes. And here it's the same thing, but for advisors that have been trained for 200 episodes. So we have plotted, we see that PPR and PI using self-transfer get a nicer result than SAC alone, so subtitle critique, the baseline alone, which is encouraging. Especially policy intersection seems to do a good job. We also have plotted dual policy distillation, but with its we use its original the original code provided with the paper by the authors, and we have plotted it on next to algorithms implemented on top of SAC. We see that so the baseline of DPD is deep deterministic policy gradient. It seems that deep deterministic policy gradient does not learn the end pi bullet environment as well as SAC, unfortunately for it. We have, of course, it's not very fair to plot dual policy distillation next to these other algorithms while it's not implemented on top of the same baseline, so it's pretty unfair to plot it there. But we have added some extra plots here that hopefully on which we can actually compare different extensions of baselines in a fair way. So what we do here, so this one, each of these correspond to the learning curve on the, we have learning curves on the left and then these extra plots on the right that show the gain, the actual gain brought by each extension to its baseline. So the extensions being dual policy distillation, PPR, and PI, to the baselines DDPG and SAC. So now we can plot them in a fair way and show that indeed doing self-transfer either with PPR or PI on the end environment seems to really help subtitle critique. We kept the configuration of the advisor that worked the best, that gave the best learning curve to plot, to not have two cluttered plots here. And DPD seems to help DDPG a bit for ANT. For Hopper, on the other hand, we see that sometimes doing self-transfer, especially with PPR, seems to sometimes worsen performance. And sometimes on half cheetah, we see that this time it's DPD that seems to endanger performance, as well as PPR. So the main takeaway is that our continuous policy intersection seems to generally, so it seems to help SAC, and if it does not help SAC, then it at least does not completely endanger performance. Okay. So this is my presentation. If you have any questions, feel free to ask on the Slack channel. I would be delighted to answer. Thank you for watching.